the better we can go through and solve a question. Okay? Because it is a chemistry class, where might be a good place to start? We can do a step above reading. Periodic table doesn't necessarily have to do anything with the question. So reading at least gets to the question. I can accept that. Okay. What type of reaction? What are we looking at? Okay. To identify that, we have to know what we reacted. To identify what reacted, what do we need? We need to know our nomenclature on what we mixed. So we have to go through and read the question and identify what was reacted. We have nitric acid and we have barium hydroxide. Does anybody just look at that and go, whoop, that's that type of reaction? No. Okay, so maybe what you need to do is start the process of writing down the chemical reaction. So what do we need to do? Write it out. So nitric acid and barium hydroxide, right? That's how we should do it? Simplify it. Put it into a format that actually makes sense and is useful. It tells us the amounts. What do we need to do? Use some formulas. Use our nomenclature skills from Chapter 6 and write down the formulas for what those things are. What is nitric acid? Yes, it is aqueous, but I'm going to pull the we don't need to worry about our phase card. Barium hydroxide. BaOH, because I have barium and I have hydroxide.
Well, parentheses on the OH.
I need two bariums because, two hydroxides because barium's a +2, hydroxide's a -1. All of that charge information that we did in nomenclature comes back and haunts you. Okay? What happens when we mix these two species? We now have to identify the type of reaction, and there's two valid types of reactions that can help us with this. We can refer to it as, what did you suggest, Brandon? A double replacement, because we have two pieces. We have a positive and a negative. We have a positive and a negative. So we could run a double replacement. Anybody else want to volunteer another guess? A neutralization, because we're reacting acids. That was our big tip-off that we're running a neutralization reaction. So if we run through our reaction, we would end up with H and OH, because it's hydrogen with hydroxide, and barium with nitrate. What is our next step? Balance the... I have to balance the formulas. In predicting the products, I've said a double replacement reactions occurred, so I've exchanged the pieces. But did I actually make sure that the exchange of those pieces was done correctly? Not yet. What is the charge on hydrogen? And the charge on hydroxide? Is that formula correct? Yes, because the charges neutralize. How about the next one? Barium's charge is +2. Nitrate's charge is -1. Is that formula correct? No, so we need to fix it. NO3, 2. Okay. When did we do all of that?
Just now.
Chapter 7. Okay. That was the whole point of Chapter 7, was identifying the reaction. So a question may come up, well, do I need this information? Okay. Yes and no. The first part of it, does this organize what the question is saying is happening? Yes. It takes English, which by God, who likes English, and turns it into, and I recorded that too, that was horrible. And it turns it into, okay, turns it into a chemical equation, something that we can look at as chemists and interpret. Right? So it takes some of that and it processes it, it analyzes it, and organizes it. Okay. Do we need it? Maybe, maybe not. But how long should that have taken us to figure out? Seconds. You're under 10 seconds to solve that. If you're not under 10 seconds to write out that chemical equation, you need to do more practice within Chapter 7. Okay, and I'm getting questions. Well, where do I find practice? Has anybody opened up the textbook? Let's try that. How many people have opened the textbook?
Well, I do it to do the homework.
Yeah, you do it to do the homework. The questions at the end of the chapter, I only assign a few of those to get you basic practice. What should you be doing if you find any of those difficult? Doing more. Okay. We now have the potential for a chemical equation. Should we be continuing on? Are we done looking at our chemical equation? The equation must now be balanced. Is it balanced? No. Whoops. What do we need to do to balance it? We need to change the coefficients. Hopefully you should be able to recognize, well, and actually I changed my mind on that. How do we go through and balance? Hydrogen. How many hydrogens on the left? I heard 1. That's an interesting question. Why 1 and not 3? Who said 1? Did you say 1? Why did you say 1?
Because you want to keep hydroxide together. Because it's
Did hydroxide change in the course of this reaction? No. So I don't have to split up hydroxide into oxygen and hydrogen. I can keep it as hydroxide. Which then means how many hydrogens are on the left? Only 1. This can simplify my balancing process. How many hydrogens on the right? 1. Hydrogen's balanced. Nitrate. How many nitrates do I have on the left? 1. The 3 is part of what makes it nitrate. How many nitrates on the right? 2. Is it balanced? No. What do you do to fix it? I need to put a 2 as a coefficient. That nitrate now becomes 2. Is my nitrate balanced? Yes. Next one. What's the next one? Barium. How many bariums on the left? Barium's on the right. 1. Is that balanced? Is barium balanced? Yes. Hydroxide. 2 and 1. Is the hydroxide balanced? What should you do? We need a 2. Where do we place that 2? We put it in front. We're changing the coefficients. And this now becomes 2 hydroxides. What do we do now? Check your work. Okay? So we clearly did not do enough checking work examples because your balancing abilities have been not the greatest, to put it mildly. Ineffective. Okay? How many hydrogens do we now have on the left? 2. How many hydrogens on the right? How many nitrates on the left? How many nitrates on the right? How many bariums on the left? Bariums on the right. Hydroxides on the left. Hydroxides on the right. Is it balanced? Write it all down. Do that process. I want to see the work. Get a fresh piece of paper. Write it all out. You will be turning this in. Nope.
So why do you...
And remember I said you should be able to do it in under 10 seconds. I'll give you a minute.
Wait, what are we doing? So double replacement.
Providing the balanced equation.
Okay. How do you know...
So, we have our balanced equation now. What do we do now with that information? Okay, we could put it to work. How could we put it to work? Ping. What are we trying to do? I mean, writing out the equation was because it's a chemistry class. We just kind of assume that in a chemistry class we should look at chemical reactions.
All the questions asking what was the molarity of the nitric acid.
Okay, so what we can do is use our equation as a way to organize the information given in there, because there's a bunch of information given in there, and that could be very confusing. So, Alex, what you pointed to and said, I want to know the molarity of the nitric acid. Okay, so how could I use this equation to format that? Okay, I could say I want molarity question mark right there. Would that be useful?
No.
Why no?
Because that's not the nitric acid.
I'm writing the molarity under barium. Am I solving for the molarity of the barium? No. So is that a useful place to write that information? No. Where should I write it? How about under the nitric acid? Okay. We could put a molarity, capital M question mark. That's useful. We don't know what that is. We're trying to solve for it. Okay. What did I tell you to do every time you see molarity? Capital M. You need to be writing moles over liters. So to solve for the molarity, what do I need to know? I need to know, go ahead. I need to know the liters of nitric acid. So what could I do? Let's see if the question tells me the liters of nitric acid. Does it tell me the liters of nitric acid?
It tells you in milliliters.
It tells me the milliliters. So I don't have a direct equality here, but I have a volume. I have something that I could convert or work with. What is the volume for my nitric acid?
So 145 milliliters?
It says 745 milliliters of acid is added to the flask. Okay. What else do I need?
Conversion factor?
What do I need for molarity? We've got, and you guys all shouted out that you can do that conversion. So I'll just accept that you can do that, and we'll write it out eventually. Okay. What else do we need to solve for molarity? Remember, what are we trying to do? We need the moles of nitric acid. Okay. How do we get the moles of our nitric acid? Okay, so what we're starting to do is come up with doing a conversion here. You're saying that I'm not given that information, so I could set up a new question, okay, where I could solve for the moles of nitric acid. Oh, and you suggested the periodic table can give me a gram per mole value. I don't even know what it is, but let's just come up with a number here. Where would I put the mole value in my gram per mole value? Should it go in the numerator or the denominator? Why should it go in the numerator? In our answer, moles is in the numerator. Grams would show up on the bottom. Right? So oxygen 16 times 3, 48, 14, 15.
63.
Thank you. Wow, that was good. 63 grams in 1 mole. I now have a conversion factor. This would get me to moles of nitric acid. For those of you panically writing this down, are we given the grams of nitric acid? No. So while this is a potential way to solve for the moles of nitric acid, are we given the information that allows us to get there? No. Okay? So that conversion doesn't work for us, which means I need a different conversion factor. I need to be able to get the moles of nitric acid from something else. Okay, because I think, are you asking a question or making a statement?
Kind of asking a question.
That makes me nervous. Okay, go for it.
In the balanced equation?
Shh. What were you going to ask?
I was going to ask, I was going to suggest.
What are you going to suggest?
22.4 liters equals 1 mole.
So 22.4 liters equals 1 mole. Okay, that brings in volume. And volume we said we will completely ignore until we've talked about it. What's our volume unit that we've brought in so far? molarity. The 22.4 liters is 1 mole is a perfectly valid conversion for gases. None of these are gases, so that doesn't work. Okay, so that's where we have to be very, very careful in separating. That's why I hate that conversion factor, because you think, oh, I can use it. No, you can only use it in a gas. Okay, so it should be used appropriately.
So if this turns into a gaseous thing, we would use it.
Then we could deal with it, but we aren't there, so we won't worry about it.
So
We aren't there, so we won't worry about it. So now we got to come up with another conversion factor. Can I relate the moles of nitric acid to anything else?
yes, the balance equation.
Atoms, number of atoms.
But wait,
As Hunter just suggested, can I relate the moles of nitric acid to some other species? Say like the barium hydroxide that it reacted with. And we know it reacted with it because
it changed color.
we wrote out a balanced chemical reaction. Oh, maybe that's why we were trying to provide that. That gives me not only a way to organize my data, but it also gives me a conversion factor and brings that to the forefront. What is the conversion factor that needs freaking pen? I can relate the moles of nitric acid to what? The moles of... Why barium hydroxide? Couldn't I relate it to water? Yeah. Why not relate it to water or the thing?
Because it's stated how much barium oxide is.
Do I know something about those three species? Do I know the thing? I know what it made it, but do I know anything about it? No. So there's no information that I could list for that. Water, I know it was made. Do I know how much of it was made? No context given on that. Barium. Am I given some information about the barium hydroxide?
Yes.
What am I given about it?
A mole to liter ratio. Mole to milliliter.
I'm given 0.200 molar, which we said was a horrible thing to write, and we should instead write moles per liter. And what else am I given? I'm given the volume of my barium hydroxide as
165 milliliters.
165 milliliters. So I'm given a lot of information about the barium hydroxide. I'm not given any information about the water or the thing, whatever the thing may be. So by organizing this and putting that information down, when we go to actually solve, we can say, oh, I've got that. Oh, I don't have that. I can relate the moles of nitric acid to the grams of nitric acid using the periodic table, but I'm not given grams of nitric acid. I am given something about the moles of barium. Can I relate the moles of nitric acid to the moles of barium hydroxide? Yes. Where does that relationship come from? The balanced equation, which you all wrote down 5 minutes ago. What are the coefficients that need to go into this? 2 nitric acids to 1 barium hydroxide. This is now setting me up. I have a conversion factor. Well, is that one valid? Right? Do I have information about the moles of barium? Moles? That one? Am I given information about the word in red in the question?
Yes.
Do I see moles of barium hydroxide show up anywhere else?
Yes.
Yeah, I am. So let's use that information. We want to use it to do what to this unit? Make it go away. Which means in that conversion factor, what unit needs to show up on top?
0.2.
What unit needs to show up on top? Moles of barium hydroxide. What unit should show up on the bottom? Unit? Unit? What can we convert moles of barium hydroxide to? Moles per liter. What unit needs to show up on bottom? Liters. Well, not the rest of the class said that. And you also said something else. Do I have numerical values that can be tied to this?
Yes.
Yes. What numerical value is tied to liters? 1. What numerical value is tied to moles? Oops. What happens? The moles cancel. Do I have my answer? No. So what do I need to do? I need to get rid of the liter unit. Okay. Am I given the liters of my barium hydroxide?
Yes, but not directly.
Not directly. I'm given milliliters. So what do I need? To convert liters to milliliters. What is that conversion? Milli is 10 to the negative third. Is 1 milliliter. I know if you want to do a different one, that's fine. Go ahead and do it. Just that's what I'm going to show you here. Okay. Liters cancel. Am I given milliliters? What is the milliliters I'm given? 165. Why is it not the 745? The 745 was tied to nitric acid. And I'm canceling the liters of barium hydroxide. What unit would I now have at the end of all of this calculation? Milliliters cancel, so no milliliters. Liters cancel, so no liters. Moles of barium hydroxide cancel, so no moles of barium hydroxide. Moles of nitric acid. What was I trying to solve for? Oh, snap, there it is. Okay. What do I now do with that information? Was that what the question asked for? What did it ask for? Molarity. How do I solve for the molarity? I can take my moles and divide it by my liters. Am I given liters? No, so I'm given milliliters, so I have to convert the milliliters into liters. And you can do that in your head if you would like. Yeah. Yes, that's mathematically how it calculates out. Okay. When did we look at all of these? Nomenclature, chapter 6. Reactions, chapter 7. Moles, kind of indirectly, we kind of skipped chapter 8. Okay. Chapter 9, chemical reactions and moles. Okay, how we manipulate those. Chapter 13, molarity. 4 chapters. All 4 chapters we have covered already. You are required to synthesize and put these pieces together. How many of you wrote down all the steps that we went through to solve this? Oh, one person. Interesting. Believe it or not, there's actually 2 people that wrote it down. The other person is all behind us.
I tried to keep it as clean as I could. It's my best attempt.
Wow.
Process, right?
This is the process that you are working through every single time. And one of the issues that you tend to think about is say, well, I need to follow exactly that. Okay? Follow exactly that with sulfuric acid. Is that a new question?
Yes.
Yes, it's the pieces that you need to be following. It's the processing steps that you're thinking about through it. I can repeat that. Nitric acid. We need to be able to apply and put into this, but it's the individual process of going all the way through and looking at it. Every single one of these steps you have done. None of these steps are new. Okay? The issue that I think is happening is you're doing this one step and saying, okay, I'm fine with one step, and then you aren't testing yourself. How do you test yourself?
Very careful.
Do another question and another question. When you consistently get a question right, then you've done it appropriately. Okay? If you are not continually testing yourself, you will not get the process. Okay? Yes?
Do you have more questions like this that we can keep everything?
Oddly enough, Naya, help me out. What slide?
24.
I don't know why I asked that because I just have to do this anyway. Whoop. Concept that we're supposed to be covering this week, limiting reactants and percent yield. Look at the question asked. That looks relatively straightforward. That actually looks shorter than the last one. I went through and broke it down to the steps of the question that you actually need to answer. We need to figure out the formula for magnesium hydroxide and hydrochloric acid. What did we do as step 1 in the last one? Nomenclature. What is step 1 here? Nomenclature. Huh, interesting. Step 2. Type of reaction that occurred. When you mix those reagents, what happens? That's exactly what we did with that last question. What products were yielded? Exactly what we did. We balanced the equation. Exactly what we did. Okay. Maximum yield, officially that's where we stopped. All this other stuff is new to limiting reagents. Okay. So what we did was 1, 2, 3, 4, 5 steps as a process. Greg broke that down into an entire board worth of steps. Okay. This is what you need to be thinking about and approaching. Taking pictures of this slide is fantastic, and I'm not going to complain about that. Except you already have the slide. There is no need to take a picture of it because you already have the material. Okay? You need to be practicing. If it sounds like a broken record, that's probably because you're going to keep hearing that statement for the rest of the lectures. You can probably start counting the number of times. Instead of counting how many times I do theoretical or ideally, you can count the number of times I tell you to practice. Okay? So, with that concept, let's take a deep breath and start Chapter 10. Chapter 10 is all about gases. Okay. And really, I would say we can cover it in 5 minutes, but it's a bit of a whirlwind, so we'll go through kind of the basics behind it and kind of leave it at that, and then we'll pick that up on Thursday. Properties of gases. You already know these. Okay? And because you already know these, and I'm assuming you can't read fast enough, what are our properties of gases?
Don't have a shape.
No shape, or variable shape.
Low density.
No, or low density. Okay, we'll kind of address a different issue there.
22.4 compressed.
They can be compressed. Okay, when they get compressed, are they compressed uniformly or do they just wobble all over the place?
It's varied.
They compress very uniformly.
Because, yeah, that you can,
Yes.
that's the whole thing with, like, if you compress a gas, it'll go back to a solid state.
Kind of like that, yes. Okay. So variable shape, volume, they expand and compress uniformly, very low densities, and they mix uniformly. These are all standard properties of gases. Okay. This is a good slide to bring in. Where do we start with this one? People wonder why I say ideally a lot. Guess what we do in science? We look at the ideal system. Why do we not look at real systems? Because real systems are stupidly difficult and hard to work with. That's why we ignore real systems and we come up with the best approximation we can, which is our ideal systems. When we're looking at gases, we've got some pretty big assumptions that go into them. Number one, they are super tiny molecules. So tiny that we say an individual gas particle occupies no volume. Okay. So if we were to measure the volume of this room, how would we do it? Length times width times height. Okay. When we bring in a single person, does the volume for the next person change? Yeah. Why does it change? How much does it change by?
One person.
The volume of the one person that's already there. Okay. So when we bring in a whole bunch of people, we've reduced the volume of the overall sample, which means those people can't exist in the same place. When we're looking at ideal gases, we actually say that when we add more people to the room, the volume doesn't change. It stays exactly the same. Because we're saying the particle does not occupy space. Does that make sense when we're looking at a gas? Well, what was the density of our gases? Incredibly low. So for a given volume, the likelihood of finding any particle or any molecule is so low that the odds of finding two particles at the exact same location even lower. Okay? So we end up making that flat assumption off the top. After that, molecules demonstrate rapid motion, single straight lines, okay, and in random directions. Okay? There's no order behind how they move. They don't say, oh, well, I like the left-hand side of the container, so I'm going to move over there a lot. Okay? No, it moves whole place, and it's only going to go in a straight direction. Okay? We don't get like drunk molecules spinning in loops. Okay? Gas molecules have no attraction for one another, okay, which is another kind of weird statement. Okay? If we looked at people, and we organized people in this room, do you guys have an attraction for one another? No? No attraction for one another? So that means when you come into this room, there's an equal probability of you sitting next to any person in this classroom, not the exact same seat and the exact same people around you? Ooh, interesting. So we might be a bit dicey there because we're saying, wait, it's not an attraction. She's just a friend. She's just a friend. We're not making that statement. We're just saying you are attracted to people that you want to talk with and interact with. Okay? We're not breaking into psychology in this case. Okay? Gas molecules don't show that. There is no attraction for one other other molecules, which is a weird statement to make again, which we'll see after exam 3. Gas molecules collide without losing energy. Okay? Which I'm sure all of you want to do. If you punched me, okay, eventually your hands are going to start to hurt. Okay? I work out, man. I got an adamantium skeleton. You just can't see it. Okay? Our gas molecules, when they come in, they hit and they bounce completely off. Defined. The last one's kind of a weird one. The kinetic energy, so the amount of motion of our individual particles, is directly proportional to the temperature. Which means the hotter it gets,
The more aggressive the molecule.
aggressive is a bit of an odd term. It starts to personify it, but yes, the more it moves. The lower the temperature, the slower it moves, okay, or the less it moves. We have a direct relationship between those. Okay, so those are our big assumptions that go into the ideal gas behavior. Okay? Because of all of this, we can end up coming to this conclusion, that a mole of any gas equals 22.4 liters. Which of those assumptions for our ideal gas really give us this conclusion? Which of our assumptions up here really get us to this conclusion? The last one says as I change temperature, it moves more.
Well, this is standard temperature.
So this is standard temperature. Am I changing the temperature? No. No, so does the last one help out? No. What are we saying? For any molecule, I don't care which molecule it is. It can be a big molecule, a small molecule. If I take a mole of those molecules, they all occupy the exact same space. It's the first assumption. Our gas molecules have no volume. Okay? Which means when I take a mole of those particles, they're all going to occupy the exact same space. They're not going to vary depending on the size of the atom. If I take a mole of hydrogen and a mole of ununoctium, I believe is what it is, 118, okay, the smallest element and the largest element, if I take a mole of them and turn them into a gas, what is the volume? It's 22.4 liters. Well, that's weird. If I took a mole of me versus a mole of Tyler, are we going to occupy the same volume? No. Why not? I'm a little bit bigger. Just a little bit. Than Tyler. What's that?
Somebody call me a shrimp.
No, I'm just doing comparisons in size. I'm just saying I'm gigantic. Okay? So these are our big assumptions that go in. This conclusion What's the big issue with this equality now? As soon as we have an equality, what do we have?
Conversion.
A conversion factor, which then means, you remember all the molarity stuff that we did? Now you can do it for gases, the exact same thing.
Solving the way for gas.
Effectively, yes.
So, but it's direct, that would be like